Hello, welcome to section 3.1, Extrema on an interval. So we've learned about calculus and taking derivatives so far. We're going to learn more skills, more tools, but we have these tools now, and now we're going to apply those tools. And this chapter is a lot about just applying what we have just learned. So when I often hear, how do we use this? Well, this is where we're going to use it. And as we get towards the end of the chapter, we'll be talking more specifically about some real world examples. So stay tuned for that. So in this one we're talking about extrema on the intervals. Extreme values, highs, lows, that type of thing. So definition of extrema. Let f be defined on an interval containing c. If one f of c is a minimum of f on the interval I, if f of c is less than or equal to f of x for all x in the interval, that means it's the lowest point in the interval. F of c is a maximum value of f on the interval I, if f of c is greater than or equal to f of x for all x, so that's the high point. The minimum and maximum of a function on the interval are the extreme values, or extrema. So the extreme values are called extrema of the function on the interval. The minimum and maximum of a function on the interval are also called the absolute minimum and the absolute maximum on the interval. So here's a max, it's the highest point on the interval, actually for the whole graph. Here's a min, lowest point. Relative max, it's a maximum, but it's not the overall biggest one because it goes on up that way. Here's a relative minimum because it keeps on going down here, but that's a low point for an interval. The extrema value theorem. If f is continuous on a closed interval AB, then f has both a minimum and a maximum on the interval. What that's saying is, on an interval, you will have a maximum value for the interval, you will have a minimum value for the interval. We're not talking from negative infinity to infinity, we're talking about a closed interval, not the open interval. Definition of relative extrema. If there is an open interval containing c, on which f of c is a maximum, then f of c is called the relative maximum of f. Or you can say f has a relative maximum at c, f of c. If there is an open interval containing c on which f of c is a minimum, then f of c is called a relative minimum of f. Or you can say that f of c has a relative minimum at c, f of c. And the plural of relative maximum is relative maxima, and the plural of relative minimum is relative minima. Relative maximum and relative minimum are sometimes called local max and local minimum. Let's go on to the next page here. It says, find the value of the derivative at each of the relative extrema. So you might recognize these are all graphs that came from my TI-89 graphing calculator. I just imported the image. So that should be familiar. So for A, right here, f of x is x minus 2 squared plus 3, which is x squared minus 4x plus 7. So it says find the value of the derivative at each of the relative maximum, or extrema. Here we have 1, and this point is located at 2, 3. So f prime of x is going to be 2x minus 4. But what's f prime of 2? That's going to be 2 times 2 minus 4, which is 4 minus 4, which is 0. So the derivative at the relative extrema here is 0. Let's try for this next one. Down here we have extrema where? So according to this graph, this would be negative pi, this would be 0, this would be pi, this would be 2 pi, 3 pi, and that's 4 pi. Let's see, so if our f of x in this case is cosine of x, f prime of x is negative sine x. F prime of negative pi is negative sine of negative pi, which is 0. F prime of 0 is negative sine of 0, which is 0. F prime of pi is negative sine of pi, which is 0. F prime of 2 pi is negative sine of 2 pi, which is, any guesses out there? Let me hear you say it. Very good. 0. In fact, f prime of 3 pi and f prime of 4 pi, negative sine of 3 pi, that's 0, negative sine of 4 pi, that's still 0. So what do we see here? What's the pattern we're seeing? Is that when we have an extreme value, min or max, and the derivative at that extreme value is what? 0. Very good. The derivative is 0 at the extreme values. So the derivative of a critical number let f be defined at c if f prime of c is 0, if f prime of c is 0 or if f is not differentiable at c, then c is a critical number. So a critical number is where your first derivative is 0 or your function, original function, is not differentiable there. It would be a critical value. Relative extrema occur only at critical numbers. So you find your critical numbers and your relative extrema will be among those numbers. So if f has a relative minimum or relative maximum at x equals c, then c is a critical number of f. So f prime of c would be 0 or not differentiable. Okay, going on to page 3. The guidelines for finding extrema on a closed interval. To find the extrema of a continuous function of f on the closed interval from a to b, use the following steps. Find the critical numbers of f in interval from, they should say, from a to b, not x to b. Evaluate f at each critical number in a, b. Evaluate f at each of the endpoints of a, b, so at the critical values and at the endpoints. The least of these values is the minimum, the greatest is the maximum. So find the extreme value of f of x equals x squared plus 2x minus 4 on the interval from negative 1 to 1. So first thing, f prime of x is going to be 2x plus 2. So 2x plus 2 equals 0. It means 2x equals negative 2 and x equals negative 1. That happens to be one of our endpoints. So we'll look at f of negative 1 is 2 times negative 1 plus 2. That's negative 2 plus 2, and that's 0. And f of 1 is 2 times 1 plus 2, which is going to be 4. So on the interval, we have a relative minimum at x equals 1. And that corresponds to negative 1 squared is 1, plus 2 times negative 1 is negative 2, minus 4, that's going to be negative 5. So we have a negative 1, negative 5. And our relative max, this is not from a critical number, it's from one of the endpoints of the interval. So our relative max is at x equals 1. And so 1 squared plus 2 times 1, that's 2, that's 3, minus 4 is negative 1. And that's it. We have our relative min and relative max for the values on this interval. Okay, pause if you'd like. I'm going to go on. Find the extrema of h of s equals 1 over s minus 2 on the interval from 0 to 1. So if we think of h of s as s minus 2 to the negative 1 power, h prime of s is going to be negative 1 times s minus 2 to the negative 2 power times just the 1 from the derivative of s. So h prime of s is going to be negative 1 over s minus 2 quantity squared down there. So where's negative 1 over s minus 2 squared going to be 0? Well, nowhere. However, where's s minus 2 equal to 0? That's where s equals 2, so that's our critical number. But notice, does not fall within the interval. So it's not in the interval. So we look at h of 0, because that's in the interval. That's going to be 1 over 0 minus 2, that's 1 over negative 2, or negative 1/2. And h of 1 is going to be 1 over 1 minus 2, that's 1 over negative 1, which is negative 1. So our relative min is going to be at x equals 0, so we're talking about 0, negative 1/2, and the relative max is at x equals 1, we're talking about 1 comma negative 1. Take that back, got those mixed up. That's bigger than this. So we'll call this relative min here, or relative max here, and min here. Okay, going to go on to the last page. Example 4. So the retailer has determined that the cost C of ordering and storing X units of a certain product is C equals 2X plus 400,000 over X, where X is between 1 and 400. The delivery truck can bring at most 300 units per order. Find the order of the size. Find the order size that will minimize our cost. Could the cost be decreased if the truck were replaced with one that could bring at the most 500 units? Explain. So our C of X would be 2x plus 4,000 x to the negative 1, which means C prime of x is 2 plus negative 1, well, let's say 400,000 times negative 1 x to the negative 2. So that is 2 minus 400,000 over x squared. So if we set this equal to 0, we'll have 2 minus 400,000 over x squared equals 0. So 2 equals 400,000 over x squared. So 2x squared equals 400,000. Dividing both sides by 2, x squared equals 200,000. So x would be equal to plus or minus square root of 200,000. So x would be equal to plus or minus, and the minus is kind of irrelevant, 447.2316. So we'll say 447. That's the only critical number we have. So we'll look at C of 1. And that's going to be 2, I'm going back to the original function, 2 times 1 plus 400,000 over 1. And that's just going to be 400,002. Yeah, I shouldn't circle it yet. And we'll look at C of 300. It's going to be 2 times 300 plus 400,000 divided by 300. That's 1,788.85. We'll look at C of 447. 2 times 447 plus 400,000 divided by 447. That gives us 1,800. Nope, I'm sorry. I got these off. Sorry, this one was the 1933.33. This one's 1788.85. Now we have C of 400. I did that because that's one end of the interval. And that's going to be 2 times 400 plus 400,000 over 400. And that's going to give us 1,800. And if we could do 500 units, what would it be if we had a bigger truck? That's going to be 2 times 500 plus 400,000 divided by 500. And that also gives us 1,800. So if we could get a bigger truck, one that holds 500 units, yes, go for that, and we'll get 447 units. And that's the cheapest cost. So, yes, get truck that can carry 500 units. And get the 447 units. Okay. Well, I hope you enjoyed this section of 3.1. We're going to go on and do some more of this stuff, and I hope you can understand some of these uses. Taking the derivative, getting that critical value is very useful. So we learned the tools, now we're applying the tools. Thank you. Send me your questions. Bye.